is 3 Atlas past the Jupiter gravity, and as we all know, Jupiter has something called a Hill radius. This is the point in space where Jupiter's gravity and the Sun's gravity essentially cancel each other out. Inside the Hill radius, Jupiter's gravity dominates. Outside, the Sun's gravity is stronger. It's the boundary of Jupiter's gravitational influence. And here's where things get interesting. 3I Atlas isn't just going to pass near Jupiter. According to current trajectory calculations, it's going to brush right against that Hill radius, just barely outside it, with a precision that's making a lot of people very uncomfortable. Why does this matter? Because the Hill radius is home to something called Lagrange points. These are special locations in space, sometimes called the solar system's parking lots, where the gravitational forces of two large bodies create stable positions. Spacecraft can loiter at Lagrange points with minimal fuel expenditure. They're ideal spots for long-term observation platforms, and 3I Atlas is heading straight for one. Hit like and subscribe for more sleepy explanation. Some people have started suggesting that maybe, just maybe, 3I Atlas is planning to drop off a probe, an exploratory spacecraft that could take up residence at one of Jupiter's Lagrange points, either to study the gas giant and its potentially life-bearing moons, or to keep watch over the inner solar system. It's the perfect vantage point. And the timing, the precision of this approach, it's raising eyebrows. But others are thinking bigger, more alarming. What if 3I Atlas isn't planning to drop off a probe? What if it's planning to use Jupiter itself? What if it's going to execute a gravity assist maneuver, a slingshot around Jupiter that completely reverses its course and sends it screaming back toward the inner solar system? And here's the part that should make your blood run cold. If it did that, if it pulled off this maneuver at exactly the right moment, it would be on a direct intercept course with Earth. Now, I know what you're thinking. That's impossible. Absolutely impossible. And if 3I Atlas is a natural object, a random chunk of ice and rock from another star system, you'd be absolutely right. Natural objects don't make course corrections. They don't execute precision maneuvers. They follow ballistic trajectories determined by gravity and momentum. Once they're on a path, they stay on that path. The laws of physics don't allow for sudden changes of direction without some external force. But what if 3I Atlas isn't natural? What if it's artificial? What if it's a modified asteroid, a hollowed-out comet, equipped with advanced propulsion systems? Then suddenly, this impossible scenario becomes merely difficult. And difficult is something that can be overcome with enough technology and energy. Let me be clear about something right from the start. I'm not going to talk about warp drives or anti-gravity or any kind of physics we don't understand. If 3I Atlas has an Alcubierre warp drive, if it can fold space-time and move faster than light, then this entire discussion is pointless. It could just turn on a dime, point itself at Earth, and arrive whenever it wants. It wouldn't need Jupiter's gravity. It wouldn't need any kind of slingshot maneuver. The fact that it's taking this specific trajectory, that it's approaching Jupiter at all, suggests it's limited by the same physics we understand. Advanced technology, yes, but still bound by the laws of the universe as we know them. So let's explore this properly. Let's look at the actual numbers, the real physics, the engineering challenges. Can 3I Atlas, assuming it has technology we could theoretically build ourselves, actually pull off a maneuver like this? And more importantly, why would it want to? First, let's understand what would be required. Right now, 3I Atlas is travelling at about 58 kilometers per second relative to the Sun. Jupiter's orbital speed is 13.1 kilometers per second. For 3I Atlas to perform a gravity assist that reverses its direction and sends it back toward the inner solar system, it needs to do something very specific. It needs to slow down dramatically before it gets to Jupiter. Here's why. A gravity assist, a slingshot maneuver, works by stealing momentum from the planet you're swinging around. You approach the planet, fall into its gravity well, whip around behind it, and get flung out in a different direction with altered velocity. But the amount of deflection you can achieve, the angle you can turn, depends on how fast you're going relative to the planet. If you're going too fast, you just zip past with a minor course change. To get a full 180-degree reversal, to completely turn around, you need to be moving at roughly twice the planet's orbital speed when you make your closest approach. For Jupiter, that means 3I Atlas would need to decelerate to about 26.2 kilometers per second before executing the maneuver. That's a required deceleration of 34.7 kilometers per second. 34.7 kilometers per second of delta V, as rocket scientists call it. That's the change in velocity required. Now let's talk about mass. We don't know exactly how much 3I Atlas weighs, but based on its estimated size, a few kilometers across, a natural comet or asteroid of that dimension would weigh somewhere around 30 billion tons. 30 billion tons of rock and ice. But if 3I Atlas is artificial, if it's been hollowed out, converted into a spacecraft, maybe it's only 10% of that mass. Maybe it's 3 billion tons. 3 billion tons still sounds like an enormous amount, and it is. Trying to change the velocity of a 3 billion ton object by 34.7 kilometers per second requires energy on a scale that's hard to comprehend. Let's start with conventional rocket technology, the kind of chemical engines we use today. Chemical rocket engines work by burning fuel and expelling the exhaust at high speed out the back. The faster the exhaust, the more thrust you generate. The best chemical rockets we have, engines like the RS-25 that powered the space shuttle, have exhaust velocities around 4 to 4.5 kilometers per second. They have a specific impulse, the measure of how efficiently they use fuel, of about 450 seconds. So what would it take to decelerate 3I Atlas using chemical rockets? The rocket equation gives us the answer, and it's brutal. To change the velocity of a 3 billion ton object by 34.7 kilometers per second, using engines with 4.5 kilometer per second exhaust velocity, you would need approximately 1.75 times 10 to the 13th power tons of fuel. Let me put that in perspective. That's 17.5 trillion tons. That's hundreds of times more mass than the entire object. It's absurd. It's impossible. You can't carry that much fuel. The fuel itself would weigh more than anything could possibly move. Chemical rockets are out. They simply don't have the performance needed for this kind of maneuver. But what about more advanced propulsion? What about ion engines? Ion engines are something we actually use today. They work by ionizing a propellant, usually xenon gas, and accelerating the ions to very high speeds using electric fields. The exhaust velocities are much higher than chemical rockets, around 100 kilometers per second compared to 4.5. That's more than 20 times faster, and because the exhaust is moving faster, you get much better fuel efficiency. So how much fuel would 3I Atlas need if it used ion engines? The calculation gives us 1.24 times 10 to the 9th power tons. That's 1.24 billion tons of propellant. That's better, much better. That's only about 40% of the estimated hollowed-out mass of 3I Atlas. That's starting to sound almost possible, except there's a problem. Ion engines produce very little thrust. They're incredibly efficient, but they're weak. The ion engines we use on spacecraft today produce thrust measured in millinewtons, thousandths of a newton. To decelerate a 3 billion ton object in any reasonable time frame, you'd need ion engines producing thrust on a completely different scale. You'd need massive power sources, probably nuclear reactors or something even more advanced. You'd need arrays of thousands or millions of individual thrusters. It's technically possible, but it's pushing the boundaries of what we could build even with very advanced technology. But there's another option, something even more advanced, but still within the realm of known physics, plasma drives. And before you think this is pure science fiction, let me tell you we're working on this technology right now. Plasma drives work by heating a propellant to extreme temperatures, turning it into ionized plasma, and then using powerful magnetic fields to direct that plasma out the back of the spacecraft at incredible velocities. There's an experimental drive called the VASIMA drive, the Variable Specific Impulse Magnetoplasma rocket, being developed right now. The concept is to use high-energy radio waves to heat hydrogen or helium into plasma, then channel it through electromagnetic fields. Current experimental VASIMA engines can achieve exhaust velocities around 50 kilometers per second. But that's just the beginning. With more advanced technology, with more powerful magnetic fields and better plasma heating, you could theoretically push exhaust velocities much higher. Let's say an alien civilization that's even moderately more advanced than us could build plasma drives with exhaust velocities around 1,000 kilometers per second. That's only about double what we're currently working toward. Not a huge leap, certainly within the realm of possibility for a species capable of interstellar travel. At 1,000 kilometers per second exhaust velocity, the fuel requirements drop dramatically. The rocket equation now gives us 1.05 times 10 to the 8th power tons. That's 105 million tons of propellant. That's still a massive amount, but it's much less than the total estimated mass of 3I Atlas. And here's the key point. We've watched 3I Atlas shed mass. We've seen its tail, its anti-tail, streaming material into space. The amount of mass we've observed it ejecting is easily in this range. If 3I Atlas has a sufficiently powerful plasma drive, if it can process 100 million tons of its own material into plasma fuel over the course of a couple of months as it approaches Jupiter, then yes, this maneuver becomes theoretically possible. The physics works. The engineering is challenging, incredibly challenging, but not impossible. Of course, there's the question of power. Running a plasma drive powerful enough to process and expel 100 million tons of material in a couple of months requires an absolutely staggering amount of energy. We're talking about more power than our entire human civilization generates in a year. Where would that energy come from? Nuclear reactors could provide some of it. Fusion reactors, if you can build them, could provide more. But to get the truly massive power levels needed, you'd probably need something even more exotic. Solar power collected over enormous areas, matter-antimatter reactions, black hole accretion. We're getting into very advanced territory, but again, we're talking about a civilization capable of building a multi-kilometer interstellar spacecraft. Power generation at this scale might be routine for them, but wait, there's another way to approach this problem, a way that requires no fuel at all. It's called aerobraking, and it's a technique we've actually used ourselves. Aerobraking involves dipping into a planet's atmosphere during a close approach and using atmospheric drag to slow down. The European Space Agency is planning to use aerobraking at Venus for an upcoming mission. The spacecraft will skim through Venus's upper atmosphere, bleeding off speed without using any propellant. It's elegant, it's efficient, and if 3I Atlas could pull it off at Jupiter, it could theoretically achieve all the deceleration it needs without burning any fuel. There's just one tiny problem. Okay, it's actually a massive problem. The speeds involved would make this extraordinarily dangerous. When 3I Atlas approaches Jupiter, it will be travelling at a relative velocity of about 76 kilometers per second. 76 kilometers per second through Jupiter's atmosphere would generate absolutely catastrophic heating. We're talking temperatures that would vaporize almost anything, and the deceleration forces would be enormous, hundreds of Gs if it dips too deep. For a natural asteroid or comet, aerobraking at these speeds would be suicide. The object would break apart, it would be torn to shreds by the forces involved. But if 3I Atlas is artificial, if it's been specifically engineered to withstand extreme conditions, if it has heat shielding structural reinforcement, maybe it could survive. Maybe. Even then, you probably couldn't achieve full aerobraking. You could probably only bleed off maybe 10 kilometers per second or so before the risk of destruction becomes too great. That would reduce the fuel requirements by about a third. Helpful, but not a complete solution. You'd still need some kind of propulsion system to handle the rest of the deceleration, so combining these approaches starts to make sense. Use the anti-tail, which we've observed and which I'll talk about more in a moment, to create a kind of magnetic sail that provides gentle deceleration over a long period. Use aerobraking to shed another chunk of velocity during the Jupiter approach, and then use plasma drives or ion engines for the final deceleration and maneuvering. It's complicated, it's pushing the limits, but it's possible. Now there's another scenario worth considering. What if 3I Atlas isn't trying to turn itself around? What if it's just trying to deploy something? A probe, an observation platform, something much smaller that doesn't require nearly as much energy to slow down and position. Let's imagine 3I Atlas wants to drop off a 10-ton satellite at one of Jupiter's Lagrange points. 10 tons is substantial. That's about the mass of the International Space Station's largest modules. It could carry significant scientific instruments, computers, power systems, everything you'd need for a long-term observation post. To insert a 10-ton object into a Lagrange point, you need to match velocities with Jupiter's orbital position. The difference in velocity between 3I Atlas at Jupiter's distance and the orbital velocity at the Lagrange point is about 48.67 kilometers per second. That's still a huge change in velocity, but for a 10-ton object instead of a 3 billion-ton object, the energy requirements are vastly lower. But how do you decelerate a probe without carrying massive amounts of fuel? You use a laser sail, or better yet, a magnetic beam system called a mag beam. Let me explain both, because they're fascinating technologies that we're actually researching right now. A laser sail works like a solar sail, but instead of being pushed by sunlight, it's pushed by a powerful laser beam fired from the mothership. The sail is made of highly reflective material. Photons from the laser hit the sail and transfer momentum, providing thrust. The advantage is you don't need to carry propellant on the probe itself. All the energy comes from the laser on the main spacecraft. The problem is that photons, even very high-energy photons from a powerful laser, don't carry much momentum. They travel at the speed of light, which means they zip past the sail very quickly without transferring much of their energy. To get significant thrust, you need enormous sail areas and incredibly powerful lasers. The calculation shows that to decelerate a 10-ton object by 48.67 kilometers per second over the course of a month would require 7.3 times 10 to the 16th power joules. That's roughly equivalent to a 15 megaton nuclear explosion. That's an insane amount of energy for a relatively small maneuver. It's inefficient, but there's a better way. A mag beam. This is a concept developed by Robert Wingley and actually funded by NASA in the early 2000s. Here's how it works. The main spacecraft generates a powerful collimated beam of ionized plasma. This creates an artificial magnetic field. The probe carries a magnetic sail, essentially a loop of superconducting wire that generates its own magnetic field when current flows through it. When the plasma beam hits the magnetic sail, the two magnetic fields interact. The sail creates a mini magnetosphere that deflects the incoming plasma ions, just like Earth's magnetic field deflects the solar wind. And because the plasma particles are much more massive than photons and travel much slower, around 40 kilometers per second instead of the speed of light, they transfer far more momentum to the sail. The efficiency difference is dramatic. To achieve that same 48.67 km per second deceleration, for a 10-ton probe using a mag beam requires only about 9.7 times 10 to the 12th power joules. That's 7,500 times less energy than a laser sail. With a 300 megawatt plasma thruster on 3i Atlas, you could accomplish the entire maneuver in just 9 to 14 hours of continuous beaming. If you spread it out over a month to provide gentler deceleration, the average power requirement drops to just 3.7 megawatts. That's comparable to a few wind turbines or a small coal power plant. For an advanced civilization, that's trivial. That's nothing. Deploying a probe to Jupiter's Lagrange points using this technology is not just possible, it's actually relatively easy. But could you use the same kind of system to decelerate 3i Atlas itself? Could you build a magnetic sail large enough to slow down the entire multi-billion-ton spacecraft? In theory, yes, but you'd need an absolutely massive sail. And it would need to interact with something, with the solar wind probably. The sun constantly emits a stream of charged particles, the solar wind, that flows outward through the solar system. A magnetic sail could push against this wind, using it for propulsion or deceleration. The problem is that the solar wind is very weak, especially far from the sun. At Jupiter's distance, even with a magnetic sail millions of kilometers across, you'd only achieve about 1 kilometer per second of deceleration over the course of a month. That's not nearly enough. However, if you sustain this over a couple of years, you could potentially decelerate 3i Atlas enough to be captured by the sun's gravity, changing its trajectory from hyperbolic to elliptical. And here's where things get really interesting. Remember that anti-tail we've been observing? That massive structure streaming out from 3i Atlas toward the sun, defying the solar wind, maintaining coherence over distances of 500,000 to 1 million kilometers. What if that's not just a passive dust feature? What if it's an active system? What if it's a giant magnetic sail? If the anti-tail is composed of charged particles, ions held in place by powerful magnetic fields generated by 3i Atlas, then it would function exactly like a mag sail. It would be a massive magnetosphere, a bubble of magnetic field expanding over enormous distances, interacting with the solar wind. And 3i Atlas could use it for propulsion. It could orient the anti-tail to drag against the solar wind, providing deceleration without requiring any propellant. This would explain so many of the anomalies we've observed. The anti-tail's unusual collimation, the way it maintains its structure despite the solar wind, the symmetric jets that seem to be feeding it with material. If the anti-tail is an artificial magnetic structure, all of these features make sense. They're not bizarre, natural phenomena defying physics. They're engineered systems doing exactly what they're designed to do. You could combine this with other deceleration methods. Use the anti-tail mag sail to provide gentle, continuous deceleration over months or years. Use aerobraking at Jupiter to shed additional velocity. and use plasma drives for final course corrections and maneuvering. Layer these technologies together, and suddenly the impossible starts looking merely difficult. But there's still the question of power. Where does the energy come from to run all these systems? Plasma drives need enormous amounts of electricity. Magnetic field generators need power. Even if you're using passive systems like mag sails, you need energy to create and maintain the magnetic fields. Here's a wild thought. What if the antitail itself is a power generation system? Stay with me here. What if the antitail is partially composed of nanomachines, microscopic robots that can absorb solar energy and transmit it back to 3i Atlas? It sounds like science fiction, but it's actually theoretically possible with advanced nanotechnology. Imagine billions or trillions of tiny solar collectors distributed throughout the antitail's volume. Each one captures sunlight and converts it to electricity. Then they beam that energy back to the main spacecraft using microwaves or lasers. The antitail is enormous, millions of kilometers long, with a cross-sectional area that could be tens of thousands of square kilometers. The amount of solar energy hitting that area is staggering. Let's do the math. Assume only 1% of the antitail's volume is filled with these nanomachines. Assume they're only 1% efficient at capturing and transmitting solar energy. Even with those conservative assumptions, the antitail could harvest about 1 petawatt of power. 1 petawatt. That's 1 quadrillion watts. That's 50 times more power than all of human civilization currently generates. Over the course of a month, that would provide 2.6 times 10 to the 21st power joules of energy. That's comparable to the kinetic energy of a large asteroid impact. It's comparable to the output of millions of nuclear reactors. It's more than enough to power any kind of propulsion system 3i Atlas might need. Plasma drives, ion engines, magnetic field generators, all of it could run continuously with power to spare. So we've established that the physics works. The engineering is extraordinarily challenging, but with sufficiently advanced technology that's still based on principles we understand, 3i Atlas could theoretically execute this maneuver. It could decelerate. It could use Jupiter for a gravity assist. It could reverse course and head back toward the inner solar system. But why? Why would anyone do this? That's the question that really matters. Because even if something is possible, that doesn't mean it makes sense. If 3i Atlas wanted to study Earth, if its mission was to make close approaches to our planet, why didn't it do that earlier? Why didn't it execute a slingshot maneuver around the Sun at perihelion? The Sun's gravity is far more powerful than Jupiter's. A solar slingshot would have been much more efficient, requiring far less fuel and energy. So why wait? Why choose Jupiter instead of the Sun? The answer, when you think about it carefully, is actually obvious, and it's the answer that should concern us the most. Look at 3i Atlas's trajectory through the inner solar system. It passed close to several planets. Venus, Mars. Jupiter's orbit brings it near several of Jupiter's potentially habitable moons, Europa, Enceladus, worlds that might harbour life beneath their icy surfaces. But there's one planet it didn't get close to, Earth. 3i Atlas's trajectory took it nowhere near our world. It observed us from a distance, certainly. With advanced sensors, it could have studied us in detail from millions of kilometers away. But it never made a close approach, until now. If 3i Atlas executes a slingshot around Jupiter and reverses course, its new trajectory would bring it directly toward Earth. It would intercept our planet on its way back through the inner solar system. Earth is the last major planet on its checklist, the final world it hasn't examined up close, and the Jupiter slingshot puts it on the perfect trajectory to complete that examination. But there's another reason, a more subtle one. By waiting until now, by approaching Jupiter instead of slingshotting around the Sun at perihelion, 3i Atlas's hypothetical builders get something valuable. They get to observe us first before deciding whether to approach. They get to watch how we react to their presence. They get to see our level of technology, our level of organization, our capabilities and intentions, and then, with that information, they can decide whether a close approach to Earth is safe, or desirable, or necessary. Think about it from their perspective. You're an advanced alien civilization. You've sent a probe to explore a star system. You detect signs of intelligent life on one of the planets, radio signals, light pollution, chemical signatures of industrial activity. You want to study this civilization more closely, but you don't know if they're hostile. You don't know if they have the capability to intercept or destroy your probe, so you adopt a cautious strategy. You approach the system on a trajectory that brings you close to the other potentially interesting worlds first. You study Venus, Mars, Jupiter's moons, you gather data on the system's planets and resources, and all the while, you're watching that planet with the intelligent life. You're monitoring their transmissions, you're observing their technological development, you're assessing the threat. And only after you've gathered that intelligence, only after you've determined that either they're not a threat or that the scientific value outweighs the risk, only then do you commit to a close approach. You use the outer planet, Jupiter, to reverse course and come back for a final, detailed examination of the one world you haven't yet visited. The one world that might answer the most important questions. The one world where intelligence has arisen. That's the logic. That's the strategy. And it's exactly what a careful, methodical, scientifically oriented alien civilization would do. It's not reckless. It's not random. It's prudent. It's smart. And the fact that 3i Atlas's trajectory seems to follow this pattern, that's what should keep you awake at night. Because if this interpretation is correct, if 3i Atlas is indeed artificial, and if it is planning to use Jupiter for a course reversal, then we need to prepare ourselves for what comes next. In the months following the Jupiter encounter, if this maneuver happens, 3i Atlas will be on its way back. Back toward the inner solar system. Back toward Earth. And we'll finally get answers to the questions we've been asking since July of 2025 when this object was first discovered. Is it natural or artificial? Is it a random chunk of interstellar debris or a deliberately sent probe? Are we alone in the universe or are we being watched? These questions, which have haunted humanity for generations, might finally be answered, not with radio signals from distant stars, not with mathematical proofs about the probability of life, but with a physical object, right here in our solar system, demonstrating through its actions what it truly is. And that brings us to the present moment. Right now, 3i Atlas is racing toward its rendezvous with Jupiter. Astronomers around the world are tracking it, measuring its position, calculating its trajectory. Everyone is watching to see if anything unusual happens, any deviation from the predicted path, any sign of course correction or deceleration, any evidence that this object is doing something no natural object should be able to do. The next few months are critical. They're the test. They're the moment when theory becomes reality or collapses into fantasy. If 3i Atlas simply flies past Jupiter on its predicted trajectory, maintaining its hyperbolic path out of the solar system, then maybe all these speculations are wrong. Maybe it really is just a very unusual but ultimately natural comet. Maybe the anomalies have explanations we haven't found yet. Maybe we're letting our imaginations run wild, seeing patterns where none exist. But if something changes, if 3i Atlas slows down, if it alters course, if it drops off a probe or executes a slingshot maneuver, or does anything that natural objects don't do, then everything changes. Then we know. Then the speculation ends, and the real work begins. The work of figuring out who sent it, why they sent it, what they want, and what we should do about it. This isn't science fiction anymore. This is happening right now. The object exists. The trajectory is real, the Jupiter encounter is scheduled, and in a matter of months, possibly weeks, we're going to find out if we're witnessing the most important astronomical event in human history, or just an unusually interesting interstellar comet passing through our neighbourhood. Either way, 3i Atlas has already taught us something valuable. It's taught us that the universe is stranger than we thought, that interstellar objects can display behaviours and features that challenge our understanding, that the boundary between natural and artificial might be blurrier than we assumed, and that we should never, ever say something is impossible just because we haven't seen it before. When someone tells you that 3i Atlas can't possibly execute a Jupiter slingshot, that the physics doesn't allow it, that the energy requirements are too high, you can point to the calculations I've just walked you through. You can show them that with technology we could theoretically build ourselves, maybe not today, but within a few decades or centuries, this maneuver is achievable. Difficult, yes. Extraordinarily challenging, absolutely. But not impossible. And if we, a civilization that's barely begun to explore our own solar system, can conceive of ways to do this, then an alien civilization with thousands or millions of years of additional development could certainly do it. They might have propulsion systems we haven't imagined, power sources we can't yet build, materials and engineering techniques that make our best efforts look primitive. For them, what seems impossible to us might be routine. That's the humbling part of all this. We're forced to confront our own limitations, our own assumptions about what's possible. We're forced to expand our thinking, to consider scenarios that seem outlandish until you actually work through the math and realize they're not. We're forced to accept that we might not be the most advanced intelligence in the galaxy, that there might be others out there, older, wiser, more capable, who view the cosmos and our solar system through perspectives we can barely comprehend. 3i Atlas, whatever it turns out to be, is a teacher. It's teaching us humility. It's teaching us to question our assumptions. It's teaching us to look more carefully, to measure more precisely, to think more creatively. And it's teaching us that the universe is not done surprising us, that there are discoveries waiting, revelations on the horizon, encounters that will reshape how we see ourselves and our place in the cosmos. The Jupiter encounter is coming. The moment of truth approaches, and regardless of whether 3i Atlas is a natural comet or something far stranger, we're going to learn something, we're going to gather data, we're going to test hypotheses, we're going to push the boundaries of our knowledge, and that data, those observations, will either confirm what we think we know about comets and interstellar objects, or they'll shatter those assumptions completely. Either outcome is valuable, either outcome advances our understanding, but one of those outcomes would also change humanity forever. So let's talk about what happens next in concrete terms. What are astronomers actually looking for as 3i Atlas approaches Jupiter? What measurements need to be taken? What observations will tell us whether something unusual is happening? Because this isn't just speculation. There are specific, measurable things that would indicate artificial intervention, clear signatures that would separate natural behavior from deliberate action. First, trajectory monitoring. This is the most critical observation. Natural objects follow predictable paths determined by gravity and their initial velocity. We have extremely precise models of how gravity works. We can calculate orbital mechanics to incredible accuracy. If 3i Atlas is purely natural, its position at any given time should match our predictions within very small error margins. Those error margins account for things like outgassing from the comet, which can provide small amounts of thrust, and gravitational perturbations from other solar system bodies. But if 3i Atlas is actively decelerating, if it's firing thrusters or using magnetic sails or any other propulsion system, that would show up as deviations from the predicted trajectory. The object would be in the wrong place at the wrong time, not by a little bit, by measurable amounts that can't be explained by natural processes. Astronomers are watching for exactly this kind of deviation. They're taking astrometric measurements, precisely determining 3i Atlas's position against the background stars multiple times per week. They're comparing those positions to the calculated ephemeris, the predicted positions based on orbital mechanics. Any significant deviation, anything beyond the expected error margins, would be a red flag. It would mean something is pushing or pulling on the object in ways that shouldn't be happening. Second, velocity measurements. These come from spectroscopy, analysing the light from 3i Atlas and looking for Doppler shifts. When an object is moving toward you, its light shifts toward the blue end of the spectrum. When it's moving away, the light shifts toward red. By measuring these shifts very precisely, astronomers can determine the object's velocity along our line of sight. If 3i Atlas is decelerating, its velocity should be changing in ways that don't match natural orbital dynamics. The changes might be small, just a few kilometers per second over weeks or months, but they'd be detectable, and they'd be anomalous. Natural comets don't decelerate as they move away from the sun. They might slow down a tiny bit due to outgassing, but we're talking meters per second, not kilometers per second. Any substantial velocity change would demand explanation. Third, monitoring the anti-tail and the normal tail. We've already established that 3i Atlas's anti-tail is highly unusual. It's far too long, far too collimated, far too persistent to be explained by conventional comet physics. If the anti-tail is actually a magnetic sail or some other propulsion-related structure, then its behaviour as 3i Atlas approaches Jupiter should change in specific ways. If the anti-tail is being used for deceleration, we might see it brighten or expand. We might see changes in its orientation relative to the Sun and to 3i Atlas's direction of motion. We might see increased activity, more material being fed into the structure, more energy being expended. These changes would be visible in telescopic observations. Astronomers imaging 3i Atlas regularly would notice them. Conversely, if the antitail remains unchanged, if it behaves exactly as it has been, that tells us something different. It suggests maybe the antitail isn't an active propulsion system, or at least it's not being used for this particular maneuver. Data either way is valuable. Every observation constrains the possibilities. Fourth, looking for discrete events. If 3i Atlas is going to drop off a probe, deploy a satellite, or perform any kind of separation maneuver that would potentially be visible, you might see a sudden brightening or outburst as material is ejected. You might see a change in the overall brightness profile as the main body and the separated object begin to diverge. You might even, with high enough resolution imaging, see two distinct objects where there was previously one. Professional observatories with large telescopes could potentially resolve this. The Hubble Space Telescope, if pointed at 3i Atlas at the right time, could definitely see a separation event. Even ground-based telescopes with adaptive optics, systems that correct for atmospheric distortion, might catch it. Amateur astronomers with serious equipment could contribute. It doesn't take a billion-dollar facility to notice that a comet suddenly looks different. Fifth, searching for signals. This is more speculative, but if 3i Atlas is artificial, and if it's preparing for a major maneuver, it might be communicating, either with the probe it's deploying, or with its home civilization, or even potentially with us. Radio signals, laser pulses, modulated particle beams, any kind of deliberate transmission would be detectable if we're listening in the right frequencies at the right times. SETI researchers, the scientists searching for extraterrestrial intelligence, could point their radio telescopes at 3i Atlas and scan for signals. The Allen Telescope Array in California, the Green Bank Telescope in West Virginia, the Parkes Telescope in Australia, these facilities could search for transmissions. Even if nothing is detected, that's information. It tells us either there are no signals, or they're using frequencies or modulation schemes we're not monitoring, or they're maintaining radio silence for their own reasons. Sixth, and this is the long-term observation, watching what happens after the Jupiter encounter. If 3i Atlas simply continues on its hyperbolic trajectory out of the solar system, if its path through Jupiter's vicinity shows no anomalies, then the natural explanation remains viable. But if its trajectory changes, if it enters an elliptical orbit around the Sun, if it reverses course, if anything happens that shouldn't happen naturally, then we have our answer. The verdict becomes clear. This is why the next several months are so critical. We're in the observation window. The data is being gathered right now. And when enough data accumulates, when the trajectory is measured with sufficient precision, when the velocity changes are quantified, when all the observations are compiled and analysed, we'll know. The uncertainty will resolve. The question will be answered, or at least much more constrained than it is now. Now, let's talk about the implications if the answer turns out to be artificial. If 3i Atlas does something that proves it's not a natural object, what happens then? How does humanity respond? These are questions that don't have easy answers, but they're worth exploring because the possibility, however remote you think it is real. The first response would probably be shock and denial. Despite all the anomalies, despite all the speculation, most people, including most scientists, aren't psychologically prepared for confirmation that we've been visited by alien technology. It challenges fundamental assumptions about our place in the universe. It raises uncomfortable questions about our significance, our safety, our future. You'd see a spectrum of reactions. Some people would be thrilled, excited, vindicated. Those who've always believed we're not alone would feel their convictions confirmed. Science fiction enthusiasts would be ecstatic. The sense of wonder, of discovery, of participating in a historic moment would be overwhelming for many. Others would be frightened. The unknown is scary. Aliens with technology far beyond ours, technology capable of crossing interstellar space and maneuvering through our solar system, represent potential threats we can't assess or defend against. What are their intentions? Are they merely curious, or do they have agendas that conflict with our interests? We wouldn't know, and that uncertainty would fuel anxiety. Governments would scramble to understand and respond. Military and intelligence agencies would go on high alert, assessing potential threats, developing contingency plans. Space agencies would redirect resources toward observation and potentially interception if that's deemed necessary or possible. International cooperation would suddenly become critical because this wouldn't be one nation's problem, it would be humanity's problem. The scientific community would mobilize like never before. Every major observatory on Earth would be pointed at 3i Atlas. Space telescopes would be retasked. Data sharing would become immediate and comprehensive. The goal would be to gather as much information as possible before the object moves out of optimal observation range. Every spectrum, every image, every measurement would be precious, potentially containing clues about the object's origin, purpose, and capabilities. There would be debates, fierce debates, about whether to attempt communication. Some would argue we should try to send messages to 3i Atlas, radio signals or laser pulses, attempting to establish contact. The message might be simple, mathematical sequences that demonstrate intelligence, or more complex, encoding information about humanity and Earth. The argument would be that this is a once-in-a-lifetime opportunity, that we must try to communicate with whoever or whatever created this probe. Others would argue strenuously against this. The dark forest hypothesis I mentioned earlier would be invoked, the idea that revealing ourselves, making our presence and capabilities known, could be dangerous. What if 3i Atlas's creators are hostile? What if drawing their attention is a mistake we can't undo? Better to observe silently, to gather intelligence without exposing ourselves, at least until we know more. This debate has been ongoing in the SETI community for decades. If we detect an alien signal, should we respond? There's no consensus. Some say yes immediately, others say wait, study, discuss as a species before taking such a momentous step. With 3i Atlas, the debate would become urgent and immediate because the object is here, in our solar system, potentially on approach to Earth. Then there are the religious and philosophical implications. Many religions would need to reconcile their teachings with the reality of extraterrestrial intelligence. Some theological frameworks can accommodate this easily. The universe is vast, God created it all. Life on other worlds is simply more of God's creation. Other frameworks might struggle more, particularly those that place humanity at the center of creation, or that have specific narratives about our unique relationship with the divine. Philosophers would grapple with questions of consciousness, intelligence, personhood. If 3i Atlas is an artificial intelligence, a machine mind piloting the probe, does it have rights? Is it a person? Can we communicate with it in meaningful ways? If it's controlled by biological aliens from light years away, receiving instructions or programming from a civilization we can't reach, what does that mean for concepts like agency and autonomy? The cultural impact would be enormous. Art, literature, film, music, all would be transformed by the confirmation that we're not alone. The themes that science fiction has explored for a century would suddenly become science fact. How we tell stories about ourselves, about our place in the cosmos, would fundamentally change. We'd shift from a species wondering if we're alone to a species knowing we have neighbours, however distant. Economic impacts would follow. Space-related industries would boom. Suddenly, space exploration wouldn't just be about science and prestige, it would be about survival and participation in a larger cosmic community. Governments and private entities would pour resources into space technology, into propulsion research, into communication systems. The space race of the 1960s would look quaint compared to the mobilization that might follow. There would be opportunists and charlatans, of course. People claiming to channel messages from the aliens, to understand their intentions, to have special knowledge. Conspiracy theories would multiply. Some would claim governments are hiding information, that there's been contact we're not being told about, that deals have been made. Separating truth from fiction would become increasingly difficult in an information-saturated, speculation-filled environment. But beneath all of this, beneath the chaos and excitement and fear and wonder, there would be a fundamental shift in human consciousness. We would know, with certainty, that we are not the only intelligence in the universe. That realization, once fully absorbed, would change us. It would change how we see ourselves, how we approach our problems, how we think about our future. Some argue it would unite humanity. Faced with the reality of others out there, our petty differences, our national and ideological conflicts might seem less important. We might recognize ourselves as one species, one civilization, with common interests in a larger cosmos. That's the optimistic view. The pessimistic view is that it would create new divisions. Nations and groups would compete for advantage, trying to establish relationships with the aliens or their technology, trying to gain access to knowledge or capabilities that could provide power. The inequality and conflict that plague human society would simply extend into this new domain. Reality would probably be somewhere in between, some cooperation, some competition, some wisdom, some foolishness. Humans being humans, but in a new context, responding to a challenge and opportunity unlike anything we've faced before. Now let's come back to the specific scenario we're discussing. Let's assume 3I Atlas does execute a Jupiter slingshot and begins heading back toward the inner solar system. Let's assume it's on a trajectory that will bring it close to Earth. What would that look like? What would happen as it approaches? First, there would be time. Space is vast. Even after the Jupiter maneuver, 3I Atlas would be months away from Earth. That gives us time to prepare, to observe, to decide how to respond. The approach wouldn't be a sudden surprise. We'd watch it coming, tracking its position day by day, refining our predictions of exactly when and how close it would pass. Assuming the closest approach brings it within, say, a few million kilometers of Earth, roughly 10 times the distance to the Moon, we'd have unprecedented opportunities for detailed observation. Telescopes that could barely resolve any detail when the object was farther away would be able to see surface features, if there are any. Spectroscopy would provide detailed chemical composition data. Radar could potentially map the surface, determining shape and rotation. If 3I Atlas has any active systems, any emissions or transmissions, they'd be much more detectable at close range. Radio telescopes would scan continuously. Infrared telescopes would look for heat signatures that might indicate internal power sources. Optical telescopes would search for any signs of structure, anything that looks artificial rather than natural. There might be public viewing opportunities. While magnitude 16.7 objects like we discussed with the opposition surge require serious amateur equipment, an object at close approach to Earth would be much brighter. Depending on how reflective it is and exactly how close it comes, 3I Atlas might be visible in large amateur telescopes or even binoculars. People around the world might be able to see with their own eyes or modest equipment this visitor from another star system. The media coverage would be constant and intense. News networks would have special segments, expert panels, countdown clocks. Social media would be saturated with images, speculation, theories. Everyone would have an opinion. Everyone would be watching. It would be the biggest story in the world, dominating headlines for weeks or months. And then, if 3I Atlas passes by and continues on, if it doesn't stop or orbit or do anything else unusual, we'd watch it recede. We'd track it as it moves away from Earth, back out toward the outer solar system, or perhaps settling into an elliptical orbit that keeps it in our neighborhood. We'd continue observing as long as possible, gathering every bit of data we can before it becomes too faint to detect. But there's another possibility, one that's both thrilling and terrifying. What if 3I Atlas doesn't just pass by? What if it slows down? What if it enters orbit around Earth? That would be unambiguous. That would be proof beyond any doubt that the object is artificial, and that its mission involves our planet specifically. An alien probe in Earth orbit would be the most significant event in human history. Period. Nothing would compare, not the invention of writing, not the Industrial Revolution, not the discovery of nuclear energy, or the Internet. An artificial object from another star system in orbit around our world would redefine everything. The immediate questions would be practical. Is it safe? Can it harm us? Should we try to reach it? Send a spacecraft to intercept it? These would be decisions requiring international cooperation because the implications affect everyone. You couldn't have one nation unilaterally deciding to approach or interfere with an alien probe. The consequences could be global. There would be calls to destroy it, shoot it down before it can do whatever it's here to do. Military-minded individuals would argue this is the safest course, eliminate the unknown threat. But others would counter that destroying it could be catastrophic. What if it's defended? What if destroying it triggers some kind of response, either from the probe itself or from whoever sent it? What if it contains information, technology, knowledge that could benefit humanity enormously, and we'd be throwing that away out of fear? The debate would be fierce and urgent because unlike a distant radio signal that takes years to travel between stars, this object is here, now, in our immediate vicinity. Decisions about how to interact with it can't be postponed indefinitely. Every day it's in orbit is a day we're choosing, actively or passively, how to respond. Assuming cooler heads prevail and we don't immediately try to destroy it, the next step would probably be attempting communication. Radio signals first, broadcast at various frequencies, attempting to establish whether the probe can receive and respond. Mathematical sequences, prime numbers, basic concepts that any technical civilization should recognize. Then perhaps more complex messages if there's any response. We might try physical approach, a spacecraft launched to rendezvous with 3i Atlas, to observe it up close, to attempt docking or at least close-range inspection. This would be technically challenging. 3i Atlas is large, several kilometers across, and it might be rotating or maneuvering in ways that make approach difficult. But with careful planning and enough fuel for maneuvering, it's doable. We've rendezvoused with comets before. We've landed on asteroids. The techniques exist. What we'd find during such a mission is pure speculation. Maybe the surface is just rock and ice, indistinguishable from a natural comet except for subtle hints of structure beneath. Maybe there are visible features, ports or hatches or antenna arrays, clear signs of artificial construction. Maybe there's nothing to see because the truly interesting parts are deep inside, shielded and protected. Would it let us approach? Would it respond to our presence? Would it communicate? These questions have no answers until we try. But they're questions that could be answered within months or years if 3i Atlas does enter Earth orbit, rather than decades or centuries if we're trying to communicate with distant civilizations across light years. There's also the question of what 3i Atlas might do once it's here. If its mission is observation, it might simply watch, scanning Earth with whatever sensors it possesses, recording data about our planet, our biosphere, our civilization, sending that information back to its creators perhaps, though transmission across interstellar distances would take years for the signal to arrive, or storing it internally to carry back if the probe is designed to return home. If its mission is more active, it might attempt communication with us directly, not just responding to our signals, but initiating contact, broadcasting messages in formats we can understand, or trying to establish two-way dialogue. The content of such messages is impossible to predict. Warnings, greetings, offers of knowledge, demands. We wouldn't know until it happens, or its mission might be something we can't anticipate. Alien motivations, alien priorities might be fundamentally different from ours. What seems logical or obvious to us might not apply to them. We'd be trying to understand intent across not just cultural differences but biological and evolutionary differences. That's hard, maybe impossible, but it would be fascinating to try. Let me address a question that's probably on your mind. If all of this is possible, if the physics works, if 3i Atlas could theoretically be artificial and could execute these maneuvers, why aren't more scientists talking about it? Why isn't this mainstream scientific consensus? The answer is actually pretty straightforward. Scientists are conservative, especially about extraordinary claims. They've been burned before by jumping to conclusions based on incomplete data. They've learned through painful experience that most anomalies have natural explanations once you understand them better, so their default position is skepticism. Show me the evidence, prove it beyond reasonable doubt. Until then, I'm assuming natural explanations. That's a healthy attitude. It prevents wild speculation from being mistaken for established fact. It maintains scientific credibility and rigor, but it also means that even when evidence starts accumulating, even when anomalies pile up, there's resistance to considering possibilities that seem too strange, too unlikely. With 3i Atlas, you have exactly this dynamic playing out. There are scientists, people like Avi Loeb, who we discussed in the first video, who are willing to publicly consider the artificial hypothesis. They look at the anomalies, they do the calculations, and they say we can't rule this out, we need to take it seriously. But they're a minority. Most of their colleagues are still in wait-and-see mode. Acknowledging the anomalies, but assuming there are natural explanations we haven't found yet. Who's right? We don't know. That's why the observations over the coming months are so important. The data will help resolve this. If 3i Atlas behaves naturally, passes Jupiter without incident, continues on its predicted trajectory, the skeptics will be vindicated. If something weird happens, if there are clear signs of artificial intervention, the advocates will be vindicated. Either way, the scientific method works. You make observations, you form hypotheses, you test them, you revise based on results. The process is self-correcting. Truth eventually emerges if you're patient and rigorous enough. But I'd argue that even discussing these possibilities, even working through the physics and engineering like we've been doing, is valuable regardless of the outcome. It exercises our thinking, it pushes the boundaries of what we consider possible, it prepares us, mentally and practically, for scenarios that might seem unlikely but aren't impossible. And here's something worth considering. Even if 3i Atlas turns out to be completely natural, even if every anomaly gets explained by conventional comet physics, the exercise hasn't been wasted. Because someday, maybe not with this object but with another, we will encounter alien technology. The statistics almost guarantee it. The universe is too big, too old, too full of stars and planets for us to be alone. Other intelligence exists, other civilizations have risen, have developed technology, have perhaps sent probes or missions into space. And when we encounter their artifacts, when we find ourselves face to face with technology from another world, we want to be ready. We want to have thought through the scenarios. We want to have frameworks for how to respond, protocols for what to do, understanding of what's possible and what's not. 3i Atlas, artificial or not, is helping us develop that readiness. Think of it as a drill, an exercise. The military run simulations all the time, practicing for scenarios that might never happen but could. Scientists do thought experiments, working through hypothetical situations to test their understanding. This is similar. By seriously considering the possibility that 3i Atlas is artificial, by working through what that would mean and how it could work, we're preparing ourselves for a reality that seems inevitable on long enough timescales. So regardless of your personal assessment of how likely it is that 3i Atlas is a probe, I'd encourage you to engage with the question seriously. Don't just dismiss it as science fiction. Look at the evidence, consider the possibilities, think through the implications. Because even if you conclude it's almost certainly natural, the exercise of considering the alternative is valuable. And if you're on the other side, if you think there's a reasonable chance 3i Atlas is artificial, I'd encourage you to also engage seriously with the skeptical position. Understand why scientists are cautious. Recognize that extraordinary claims really do require extraordinary evidence. Don't mistake speculation for proof, but also don't be afraid to speculate, to wonder, to explore ideas that push conventional boundaries. The truth, whatever it turns out to be, will emerge from data, from observations and measurements and rigorous analysis. And we're in the process of gathering that data right now. Every night, astronomers are imaging 3i Atlas, tracking its position, measuring its spectrum, documenting its behavior. Every week, our understanding improves. Every month, the picture becomes clearer. By the time 3i Atlas reaches Jupiter, by the time the critical observation window arrives, we'll have accumulated months of additional data. We'll know its trajectory with incredible precision. We'll have detailed measurements of its activity, its composition, its behavior. And that data will constrain the possibilities enormously. If there's going to be a maneuver, if there's going to be any deviation from natural orbital mechanics, it will happen soon. Within months. And when it happens, or doesn't happen, we'll know. The speculation will end. The question will be answered, at least for this object, and then we move forward with whatever that answer reveals. If natural, we celebrate a fascinating and unusual interstellar comet that's taught us a lot about the diversity of objects in the galaxy. If artificial, we brace ourselves for the most profound shift in human understanding since we first looked up at the stars and wondered what they were. Either way, we're living through an extraordinary moment. A moment when an object from beyond our solar system, carrying ice and dust and possibly secrets from another stellar neighborhood, is passing through our cosmic backyard. Close enough to study, close enough to learn from, close enough to potentially change everything. The Jupiter encounter is coming. The data will speak, and we'll listen, because that's what we do. We're explorers, questioners, seekers of truth. We don't shy away from hard questions just because they're hard. We don't ignore anomalies just because they're uncomfortable. We lean in, we investigate, we try to understand. And 3i Atlas, whatever it turns out to be, deserves our full attention and our best efforts at understanding. Because objects like this, interstellar visitors carrying information from beyond our solar system, are incredibly rare. We've only confirmed 3 in all of human history: Oumuamua, Borisov, and now 3i Atlas. Each one is a gift, an opportunity to learn about star systems we can never visit, about processes we can't witness firsthand, about the galaxy beyond our immediate neighborhood. We can't afford to waste these opportunities. We can't afford to be complacent or dismissive. Every interstellar object that passes through deserves intensive study, comprehensive observation, rigorous analysis. Because we don't know when the next one will come. It might be next year. It might be a decade from now. It might be a century. The intervals are unpredictable because these objects are travelling through vast interstellar distances, and the chances of one happening to pass through our solar system at any given time are low. So when one does appear, when we get lucky enough to detect it early and track it through our neighbourhood, we need to make the most of it, and that's exactly what's happening with 3I Atlas. Observatories around the world are dedicating time to it. Researchers are analysing the data. Papers are being written, hypotheses are being tested, knowledge is being accumulated. Now, let me take you deeper into the technical aspects of what a Jupiter slingshot manoeuvre would actually look like. Because understanding the mechanics helps us appreciate both how challenging it would be and how we'd recognise it if it happens. Gravity assist manoeuvres are one of the most elegant applications of orbital mechanics, and they're something we use regularly in space exploration. The basic principle is momentum exchange. When a small object, like a spacecraft, passes by a large object like a planet, gravitational interaction can change the small object's velocity, not just its direction, but its speed relative to the Sun. This seems counterintuitive at first. How can gravity, which is a conservative force, add or subtract energy? The answer is that energy is conserved in the planet spacecraft system, but the planet is so massive that the tiny amount of momentum it gains or loses is negligible, while the spacecraft's velocity changes significantly. Think of it like a tennis ball bouncing off a moving train. From the perspective of someone standing on the ground, if the ball approaches the train head-on, it bounces back much faster than it arrived because it essentially got hit by the train. The train barely slows down at all because it's so massive, but the ball's velocity relative to the ground changes dramatically. Gravity assists work on the same principle, just with gravity doing the hitting instead of a physical collision. For 3I Atlas to use Jupiter for a slingshot that reverses its course, it needs to approach Jupiter from a very specific angle and at a very specific velocity. The geometry has to be precise. You can't just fly past any old way and expect to turn around. The trajectory needs to bring the object around behind Jupiter, relative to Jupiter's orbital motion, and then fling it back the way it came. Calculating this requires sophisticated orbital mechanics. You start with 3I Atlas's current position and velocity. You propagate that forward in time, accounting for the gravitational influence of the Sun, Jupiter, and to a lesser extent the other planets. You determine where 3I Atlas will be when it reaches Jupiter's vicinity. Then you calculate what trajectory through Jupiter's gravitational well would produce the desired outcome. For a full reversal, a 180-degree change in direction, you need the object to pass very close to Jupiter. The closer you get, the sharper the turn you can achieve. But getting close to a giant planet has risks, especially at the speeds we're talking about. 3I Atlas would be moving at roughly 76 kilometers per second relative to Jupiter during the encounter. At that speed, you cross Jupiter's diameter in about 30 minutes. Everything happens fast. If the approach is too close, you risk collision with Jupiter's upper atmosphere, which extends surprisingly far from the visible cloud tops. Even grazing the outer fringes of the atmosphere at these speeds would be catastrophic for a natural object. The drag would be enormous, the heating would be intense, the object would start to break apart. But if 3I Atlas is artificial, if it's built to withstand these stresses, then atmospheric skimming becomes a feature, not a bug. As I mentioned earlier, you can use aerobraking to shed velocity without expending fuel. You deliberately dip into the atmosphere, just deep enough to create drag that slows you down, but not so deep that the forces destroy you. The European Space Agency's planned Venus mission will use exactly this technique. The spacecraft will make multiple passes through Venus's upper atmosphere, each pass slowing it down a little more, until its velocity drops enough to be captured into orbit. It's fuel efficient and elegant, but it requires precise control and robust engineering. For 3I Atlas to use this technique at Jupiter would require even more precision, because the speeds are higher and Jupiter's atmosphere is different from Venus's. Jupiter's atmosphere is mostly hydrogen and helium, very light gases, but the sheer scale of the planet means the atmospheric density extends far out. You'd need to calculate the optimal altitude precisely, balance the drag against structural limits, and execute the maneuver with incredible accuracy. If we observed 3I Atlas dipping into Jupiter's atmosphere, that would be unmistakable evidence of something unusual. Natural comets don't deliberately skim planetary atmospheres. They follow their trajectories wherever those trajectories lead, and if that happens to take them through an atmosphere, they break apart or survive by luck, not by design. So astronomers will be watching very carefully during the Jupiter encounter. They'll be tracking 3I Atlas's altitude above Jupiter's cloud tops. They'll be looking for any signs of atmospheric interaction, heating, glowing, changes in brightness that might indicate the object is passing through gas. And they'll be measuring the trajectory before and after the encounter to see if the deflection matches what natural gravity would produce or if there's evidence of additional forces. Another thing to watch for is timing. Gravity assists have to happen at very specific moments. The position of the planet in its orbit, the position of the target destination, in this case Earth, everything has to align. If 3I Atlas were natural and just happened to get deflected by Jupiter, the resulting trajectory would be essentially random from our perspective. It would go wherever the physics sends it. But if the Jupiter encounter sends 3I Atlas on a trajectory that intercepts Earth, that's suspicious. That's a low probability outcome unless it was planned. The odds of a random deflection happening to point the object exactly at our planet are very small. Not zero, but small enough that if it happens, we'd have to seriously consider whether it was intentional. Think of it this way. If you throw a ball randomly into a room full of pool tables, it might bounce off the rails and eventually sink into a pocket, but the chances of it happening on the first try are tiny. If someone claims they can throw the ball and make it sink after one specific bounce, you'd be skeptical. But if they do it, if the ball follows exactly the path they predicted, you'd have to admit they either got incredibly lucky or they actually knew what they were doing. 3I Atlas hitting a trajectory that brings it to Earth after the Jupiter encounter would be like that. Possible by chance, but unlikely enough that intent becomes the more plausible explanation. Now, let's talk about what deploying a probe at Jupiter's Lagrange points would look like. This is the less dramatic but perhaps more likely scenario if 3I Atlas is artificial and has a mission plan that involves our solar system. Instead of turning the entire multi-billion-ton object around, you just drop off a small platform and let it take up residence at a gravitationally stable point. Jupiter has 5 Lagrange points, labelled L1 through L5. L1 is between Jupiter and the Sun. L2 is on the far side of Jupiter from the Sun. L3 is on the opposite side of Jupiter's orbit. L4 and L5 are 60 degrees ahead and behind Jupiter in its orbit, forming equilateral triangles with Jupiter and the Sun. These last two, L4 and L5, are particularly stable. Objects placed there tend to stay there without much effort. 3I Atlas's trajectory will take it near Jupiter's L1 or L2 point, depending on exactly how the geometry works out. These aren't quite as stable as L4 and L5, but they're still useful. A probe positioned at L1 or L2 could observe both Jupiter and the inner solar system. It would have a perfect vantage point for long-term monitoring. To deploy a probe, 3I Atlas would need to do several things. First, separate the probe from the main body. This might involve physical separation mechanisms, springs or pyrotechnic bolts that push the two objects apart. Or it might be as simple as ejecting the probe using a small thruster. Either way, there would be a moment when one object becomes two. Second, adjust the probe's velocity to match the Lagrange point's orbital parameters. This is where the mag beam system I described earlier becomes relevant. 3I Atlas fires a beam of ionized plasma at the probe, which has a magnetic sail deployed. The interaction between the beam and the sail provides thrust, decelerating the probe until its velocity matches what's needed to remain at the Lagrange point. This process would take time, possibly hours or days. During that time, we might be able to observe the beam if it's bright enough. A collimated stream of plasma would emit light, possibly in visible wavelengths, but more likely an ultraviolet or X-ray, depending on the temperature. Space-based telescopes sensitive to these wavelengths might detect it. We'd also see the probe separating from the main body. High-resolution imaging might resolve them as two distinct objects. Their brightnesses would change as they move apart, the combined light being divided between them. And once the probe is in position at the Lagrange point, it would remain visible, at least for a while, as a faint stationary object against the background stars. Astronomers catalogue objects at Lagrange points. Jupiter's L4 and L5 points in particular, are home to the Trojan asteroids, thousands of rocky bodies that share Jupiter's orbit. A new object appearing at L1 or L2 would be noticed quickly because those regions are relatively empty and well monitored. If a 10-ton probe took up residence there, we'd detect it within days or weeks. What would such a probe do once in position? If its mission is observation, it would presumably point sensors at whatever it's meant to study. Maybe Jupiter and its moons, looking for signs of life in the subsurface oceans of Europa or Enceladus. Maybe the inner solar system, Earth in particular, monitoring our planet over long timescales. Maybe the Sun itself studying solar activity and stellar physics. It might transmit data back to 3i Atlas, or directly to its home civilization if it has powerful enough transmitters. Interstellar communication is challenging because of the inverse square law. Signal strength drops with the square of the distance, so communicating across light years requires either very powerful transmitters or very sensitive receivers, or both. But it's not impossible. We've sent signals into space. The Arecibo message in 1974, for example, was a radio transmission aimed at a star cluster 25,000 light-years away. If we can do it, an advanced civilization certainly can, or the probe might just store data internally, waiting for either 3i Atlas to return and retrieve it, or for a future mission to collect it. If the probe is meant to operate for decades or centuries, storage might be more practical than constant transmission. Either way, the presence of a probe at Jupiter's Lagrange point would be significant. It would be tangible evidence of alien technology in our solar system. Not light years away, not hypothetical, but right here, in a location we can visit if we choose to. That would change the calculus entirely. We could mount a mission to the probe. It's much closer than 3i Atlas would be after leaving the Jupiter system. Lagrange points are accessible with current propulsion technology. A spacecraft launched from Earth could reach Jupiter's L1 or L2 point in a few years using conventional rockets and gravity assists. Once there, it could approach the probe, study it, attempt communication, possibly even retrieve it or components of it. This scenario is actually more manageable than trying to intercept 3i Atlas itself. The probe would be stationary, not racing through the solar system at 58 kilometers per second. It would be small, easier to approach and study. And if it's designed to communicate or interact, it might respond to our presence in ways we can understand. Of course, this assumes the probe is benign, that approaching it is safe. There's always the possibility of defensive systems, automated responses to unauthorized approach. Science fiction is full of probes that don't take kindly to being poked and prodded, but realistically, a probe sent for scientific observation probably wouldn't be heavily armed or defensive. Its mission is to gather information, not to fight. The risk is probably manageable. The bigger challenge would be political and logistical. Who gets to approach the probe? Which nation or organization? Does it require international cooperation, a joint mission under the auspices of the United Nations or some similar body? How do you prevent one country from unilaterally claiming the probe or its technology? These are questions without clear answers, because we don't have established protocols for dealing with alien artifacts in our solar system. The Outer Space Treaty of 1967, which governs activities in space, says that celestial bodies cannot be claimed by nations, and that space exploration should benefit all humanity. But does an alien probe count as a celestial body? Probably not. Is it salvage, finders keepers? Is it property of whoever sent it, even if they're not available to assert ownership? These legal and ethical questions would need to be resolved quickly if we actually found ourselves in this situation. My guess is there would be intense negotiation, probably emergency sessions of international bodies, lots of diplomacy and posturing. Eventually, a compromise would emerge, a multinational mission, shared costs and shared benefits, with agreements about how any information or technology gained would be distributed. It wouldn't be smooth, but it would happen because the alternative, conflict or unilateral action, would be too risky. And then there's the question of what we'd find if we actually reached the probe and examined it up close. Would it be comprehensible? Would the technology be so advanced that we can't even recognize how it works? Or would there be familiar principles, engineering solutions that we can understand even if we can't replicate them yet? History offers some guidance. When Europeans encountered Chinese or Middle Eastern technology in medieval times, they often couldn't immediately understand how it worked, but they could recognize it as technology. Porcelain, gunpowder, advanced metallurgy, these were clearly manufactured, clearly the products of intelligence and skill. With study, the principles became clear and eventually were replicated. An alien probe might be similar. We might not immediately grasp the propulsion system or the power source or the data processing, but we'd recognize components, structures, systems. With analysis, with reverse engineering, we'd start to figure it out. Maybe not quickly, maybe it would take years or decades, but progress would happen. Alternatively, the technology gap might be so vast that it's like showing a smartphone to someone from the Bronze Age. They'd recognize it as an object, but they'd have no framework for understanding what it does or how. No concept of electricity, of semiconductors, of software. It would seem like magic. That's a possibility we have to consider. If 3i Atlas's creators are thousands or millions of years ahead of us technologically, their artifacts might be similarly opaque. But even magic can be studied. Even if we don't understand the principles, we can observe the effects. We can document what the probe does, how it responds to stimuli, what emissions or activities it exhibits. Over time, patterns emerge, hypotheses form, understanding grows. It might be slow and frustrating, but it's better than nothing. There's also the possibility that the probe is designed to be understood. If its mission includes contact with other intelligences, if it's meant to communicate or share information, then it might have interfaces or systems specifically built for accessibility. Pictograms, mathematical languages, modular components that can be studied in isolation. We do this with our own space probes. The Voyager Golden Records, for example, include instructions on how to play them, encoded in universal physical principles. An alien civilization might do something similar. Imagine opening a hatch on the probe and finding a display screen with simple symbols, a sequence of prime numbers, images showing the probe's star system, diagrams of its propulsion system, a greeting or message. This isn't far-fetched. If the probe's mission is to inform, to teach, to communicate, then making it accessible is logical. Of course, we're speculating wildly here. We don't know if there's a probe. We don't know if 3i Atlas is even artificial. We're exploring possibilities, walking through scenarios to understand what could happen and how we might respond. But that's valuable. It prepares us mentally and practically for outcomes that might seem unlikely but aren't impossible. Let me bring us back to the immediate future. Right now, 3i Atlas is still months away from Jupiter. Current observations show it following its predicted trajectory within the expected error margins. There have been no dramatic deviations, no obvious signs of propulsion or maneuvering. To someone looking only at the orbital data, it looks like a natural object in a hyperbolic orbit, heading out of the solar system just as physics predicts. But we've learned not to take things at face value with 3i Atlas. It looked like a normal comet at first too, until the anti-tail appeared, until the symmetric jets became apparent, until the anomalies accumulated to the point where normal no longer fit. So the fact that it's currently behaving as expected doesn't mean it will continue to do so. If there's going to be a maneuver, it would probably happen relatively close to the Jupiter encounter. You wouldn't start decelerating months in advance, because that's inefficient. You'd wait until you're in the right position, close enough to Jupiter that the timing and geometry work out, and then you'd execute. So the critical observation period is the weeks immediately before and during the Jupiter closest approach. Astronomers are preparing for this. Observing campaigns are being organised, telescope time is being allocated, international collaborations are sharing data and coordinating efforts. The goal is to have comprehensive coverage, observations from multiple sites and instruments, so that any changes or anomalies are detected and documented immediately. Amateur astronomers are also gearing up. While they can't see 3i Atlas visually at its current magnitude, those with serious equipment, large aperture telescopes and sensitive CCD cameras can contribute valuable data. There's a long tradition of amateur contributions to comet science. Some of the most detailed light curves and activity observations come from dedicated amateurs who monitor objects night after night. Social media and online communities are buzzing with discussion. People are sharing images, comparing observations, debating interpretations. It's a global conversation, driven by curiosity and wonder and the hope that maybe, just maybe, we're witnessing something historic. Even if most participants think 3i Atlas is probably natural, there's excitement about the possibility, however remote, that it might not be. This is healthy. This is how public engagement with science should work. People following along, learning about orbital mechanics and spectroscopy, and the scientific method, asking questions, participating in the process of discovery. Whether 3i Atlas is artificial or not, it's inspiring interest in astronomy and space science, and that's valuable in itself. Educational institutions are using 3i Atlas as a teaching tool. Physics classes are calculating orbital parameters. Programming classes are writing code to model trajectories. Astronomy classes are observing and analysing real data. Students are learning that science isn't just textbooks and equations, it's active investigation of the world, of the universe, using tools and methods that they can understand and participate in, and researchers are publishing papers. Not just about the artificial hypothesis, though there are a few of those, but about 3i Atlas's composition, its activity, its trajectory, all the standard scientific work that goes into characterizing a newly discovered interstellar object. These papers are building a knowledge base, documenting what we know, what we don't know, what questions remain open. This is the scientific process in action. Observations lead to data. Data leads to analysis. Analysis leads to papers. Papers lead to peer review and discussion. The community evaluates the evidence, debates interpretations, gradually converges on consensus, or identifies areas where more work is needed. It's not fast, it's not flashy, but it works. It produces reliable knowledge over time. For 3i Atlas, we're still in the early stages of this process. The object was only discovered about 7 months ago as of now. That's not long in scientific terms. Major discoveries often take years to fully understand, so we're being patient, gathering data, building models, testing hypotheses. And the Jupiter encounter will be a critical test, a moment when several hypotheses make different predictions, and observations will tell us which predictions are correct. If 3i Atlas is natural, it will pass Jupiter, get deflected by gravity in predictable ways, and continue on its hyperbolic trajectory out of the solar system. The deflection angle will match the calculations. The velocity change will match the predictions. There will be no anomalies, no surprises. It will behave exactly as a chunk of ice and rock should behave. If 3i Atlas is artificial and executing a return maneuver, we'll see deviations. The trajectory will change in ways that gravity alone can't explain. The velocity will decrease more than it should. The object might orient itself in specific ways, might exhibit thrusting or other activities. The observations won't match the natural predictions and we'll have to explain the discrepancies. And if 3i Atlas is deploying a probe, we might see separation events, changes in brightness distribution, objects where there was one before. We might detect the mag beam or other propulsion signatures. We might see something new appear at one of Jupiter's Lagrange points. These would all be observable, detectable events if they happen, so the data will speak, the observations will tell us what's happening, and then we interpret, we analyze, we draw conclusions based on evidence. That's the beauty of science. You don't have to believe anyone's claims or trust anyone's authority. The evidence is there for anyone to examine. Different people might interpret it differently, might weigh it differently, but the underlying facts are objective and checkable. I want to emphasize this because in an era of misinformation and competing narratives, the scientific approach is more important than ever. Don't just accept what anyone tells you about 3i Atlas, including me. Look at the data yourself if you can. Read the papers, check the calculations, ask critical questions, demand evidence for claims. Be skeptical but open-minded. If someone says 3i Atlas is definitely artificial, ask them what evidence supports that conclusion and what alternative explanations they've ruled out. If someone says it's definitely natural, ask them how they explain the anomalies and what observations would change their mind. Good science welcomes these questions. Bad science gets defensive or appeals to authority instead of evidence. And remember that uncertainty is okay. It's fine to say, I don't know, or the evidence is ambiguous. You don't have to have a firm opinion on everything. You can hold multiple possibilities in mind simultaneously, weighted by how likely you think they are based on current information, and be ready to update as new information comes in. That's Bayesian thinking, which I mentioned earlier. You start with prior probabilities, your initial estimates of how likely different scenarios are. Then you gather evidence. Each piece of evidence updates your probabilities. Some evidence makes one scenario more likely and others less likely. Over time, your beliefs converge toward whatever the truth is, assuming you're updating honestly based on the evidence. For 3i Atlas, different people have different priors. If you think alien probes are extremely unlikely, your prior probability for the artificial hypothesis is very low. It would take very strong evidence to move that probability up substantially. If you think alien probes are reasonably common, your prior is higher, and modest evidence might be enough to convince you. Neither position is inherently wrong. They reflect different background assumptions about the universe. But both can be updated rationally based on evidence, and that's what we're doing, gathering evidence, seeing how it affects our probabilities, moving toward truth through empirical observation. The Jupiter encounter will provide a lot of evidence. It's a critical moment, a test that will significantly update our probabilities one way or another, and I'm excited about that. Excited to see what happens, excited to learn, regardless of the outcome, because that's what this is really about. Learning, understanding, exploring the unknown. 3i Atlas has given us a gift, a mystery to solve, a puzzle to work on, an opportunity to push the boundaries of our knowledge and our capabilities. Whether it's artificial or natural, whether it's a probe or a comet, it's teaching us about interstellar objects, about our solar system, about how to observe and analyze and interpret, and about ourselves, about how we respond to the unknown, about what we hope for and what we fear. And in a larger sense, 3i Atlas is part of humanity's ongoing journey of discovery. For thousands of years, we've been looking up at the sky, wondering what's out there. We've gone from thinking the stars were tiny lights on a celestial sphere to understanding they're distant suns, many with their own planets. We've gone from wondering if we're alone to actively searching for signs of other life and intelligence. 3i Atlas is a chapter in that story. Maybe it's just a footnote, an interesting but ultimately mundane interstellar comet. Or maybe it's a turning point, the moment when we first encountered tangible evidence that we're not alone. We don't know yet, but either way, it matters. It's part of the grand narrative of human exploration and understanding, and that narrative continues. After 3i Atlas, there will be other interstellar objects, other mysteries, other opportunities. Our telescopes will keep improving. Our detection methods will get better. We'll find more visitors from other star systems, and each one will teach us something new. Maybe one of them will be unambiguously artificial. Maybe we'll detect radio signals or see clear signs of technology, or find something that leaves no doubt. That discovery is probably coming eventually, maybe in our lifetimes, maybe later, but it's coming because the universe is vast and old and full of opportunities for life and intelligence to arise. And when it happens, when we make confirmed contact with alien intelligence or their artifacts, humanity will change. We'll have to expand our sense of who we are and what our place in the cosmos is. We'll have to grapple with being part of a larger community, a galactic ecosystem of intelligences. It will be challenging and disorienting and wonderful. 3i Atlas might be the beginning of that process, or it might just be practice, a dry run, preparing us for the real thing when it comes later. But it's significant either way, so stay engaged, keep watching, follow the observations as they come in, think critically about what they mean, and be ready for the possibility, however unlikely you judge it to be, that we're living through something extraordinary. Because here's the truth that often gets lost in all the speculation and debate. We are living in an extraordinary time, regardless of whether 3i Atlas is artificial. For the first time in human history, we have the technology to detect and study interstellar objects. We can track their orbits, analyze their composition, observe their behavior. We're no longer passive observers of the cosmos. We're active participants, reaching out with our instruments and our minds to understand what's out there. 100 years ago, we didn't even know other galaxies existed. We thought the Milky Way was the entire universe. 50 years ago, we didn't know if other stars had planets. 20 years ago, we had confirmed only a handful of exoplanets. Now we know of thousands, and we know that planetary systems are common, that most stars have planets, that the raw materials for life are everywhere. The pace of discovery is accelerating. What we learn in the next few decades will dwarf what we learned in the previous century. And 3i Atlas is part of that accelerating discovery. It's giving us data we've never had before, observations we couldn't make until now, opportunities to test ideas and refine our understanding. Let me take you deeper into one aspect we haven't fully explored yet, the psychology and sociology of how humanity would actually respond if 3i Atlas does turn out to be artificial. Because beyond the scientific response, beyond the observations and measurements, there's the human response. How would people react emotionally, psychologically, culturally? We've seen hints of this already in how people have responded to the anomalies. Some dismiss them entirely, refusing to even consider the possibility of artificial origin because it's too uncomfortable or seems too unlikely. Others embrace the idea immediately, perhaps too eagerly, seeing confirmation of beliefs they already held. Most people fall somewhere in between, curious but cautious, interested but skeptical. These responses reflect deeper psychological patterns. Humans are pattern recognition machines. We evolved to see patterns, to find meaning, to make sense of our environment. This serves us well most of the time, but it also makes us prone to seeing patterns where none exist, finding meaning in randomness, jumping to conclusions based on insufficient evidence. With something like 3-Eye Atlas, this tendency can lead us astray. We see anomalies and immediately construct narratives to explain them. Alien probes, ancient artifacts, secret government knowledge. These narratives are compelling because they're simple and dramatic. They satisfy our desire for meaning and significance, but they might not be true. The anomalies might have mundane explanations we just haven't found yet. On the other hand, our pattern recognition can also alert us to genuine signals in noise. Sometimes the patterns are real. Sometimes the anomalies do point to something extraordinary. Dismissing them out of hand because they seem unlikely is also a mistake. The key is balancing openness to possibility with rigor in evaluation, being willing to consider strange ideas while demanding good evidence before accepting them. Different people strike this balance differently based on their personalities, experiences, and worldviews. Some lean more towards skepticism, requiring overwhelming evidence before accepting anything unusual. Others lean toward openness, willing to entertain possibilities on relatively little evidence. Neither extreme is ideal. The best approach is probably somewhere in the middle, combining healthy skepticism with genuine curiosity. If 3-Eye Atlas does prove to be artificial, the psychological impact would vary widely across populations. For people who are already interested in space and the possibility of alien life, it might feel like vindication. See, I told you we're not alone. There would be excitement, a sense of participating in historic events, eagerness to learn more. For people who've never thought much about these questions, it might be shocking and disorienting. The universe just got a lot stranger and more complicated. Assumptions about humanity's unique status would shatter. The comfortable fiction that we're the only intelligence in a vast empty cosmos would be replaced by the uncertain reality of a populated universe. For people with strong religious beliefs, the responses would depend on how their theology handles extraterrestrial intelligence. Some religious frameworks accommodate it easily. God created the universe. Life exists throughout it. This is wonderful and confirms divine creativity. Other frameworks might struggle more, particularly if they have human-centric creation narratives or doctrines about unique divine relationships with humanity. But history suggests that religious beliefs are more adaptable than sometimes assumed. When Galileo showed that Earth orbits the Sun rather than being the center of the universe, it challenged religious cosmology. But religions adapted. They reinterpreted texts, adjusted doctrines, incorporated new knowledge. The same would likely happen with confirmation of alien intelligence. There would be initial resistance and controversy, but eventually accommodation and integration. Culturally, the impact would be enormous. Art, literature, music, film, all would be transformed. The themes and questions that have dominated science fiction for a century would suddenly become science fact. How do we communicate with aliens? What are their societies like? What can we learn from them? What are the dangers and opportunities of contact? These questions would move from the realm of speculation to practical urgency. Artists and storytellers would have new material to work with, new perspectives to explore. The cultural production around alien contact would be massive, diverse, reflecting different hopes and fears and interpretations. Economically, there would be winners and losers. Space-related industries would boom as governments and private entities invest heavily in observation, communication, and eventually perhaps contact missions. Technologies related to propulsion, detection, analysis would see increased funding and development. Companies positioned to capitalize on this would benefit enormously. Other sectors might suffer. If alien technology or knowledge becomes available, even indirectly through study of artifacts, it could disrupt industries. Imagine if we learned propulsion principles that make current rocket technology obsolete, or energy generation methods that replace fossil fuels and even renewables. The economic disruption could be massive, comparable to past technological revolutions but potentially faster. There would also be concerns about inequality. If access to alien knowledge or technology is controlled by a few nations or corporations, the gap between haves and have-nots could widen dramatically. This is why international cooperation and agreements about sharing benefits would be so critical. The alternative, a new form of colonialism or imperialism based on access to alien artifacts, would be deeply problematic. Politically, confirmation of alien intelligence would be a wild card. It could unite humanity around common interests and shared identity as a species. Faced with the reality of others out there, our internal divisions might seem less important. We might recognize ourselves as one civilization, needing to work together to navigate this new reality. Or it could exacerbate existing divisions as nations and groups compete for advantage. The history of European colonialism, where access to new lands and resources drove competition and conflict, might repeat on a cosmic scale. Nations might race to establish relationships with aliens, or control access to their technology, seeing it as a zero-sum game where winners take all. The actual outcome would depend heavily on leadership and institutions. If international bodies like the United Nations can coordinate responses, establish norms and ensure equitable access, the outcome could be positive. If nationalism and competition dominate, it could be ugly. This is why having these conversations now, before we are in crisis mode responding to actual contact, is valuable. It gives us time to think through the issues and build frameworks. Security and defense establishments would face unprecedented challenges. How do you assess the threat level of an alien civilization when you have almost no information about their capabilities or intentions? How do you plan defenses against technologies you don't understand? How do you even think about deterrence when the power asymmetry might be overwhelming? These questions don't have easy answers. Military strategists are trained to plan for threats and develop responses. But an alien civilization that can cross interstellar space is likely so far beyond our capabilities that traditional defense planning becomes meaningless. It's like Native Americans trying to plan military responses to European colonization. The technology gap was so vast that conventional resistance was largely futile. This is a humbling realization. We might simply have to trust that alien intentions are benign, or at least not overtly hostile. Because if they're hostile and they're advanced enough to send probes across light years, we probably can't stop them from doing whatever they want. Our only real security would be in hoping they're not interested in harming us. That's an uncomfortable position for a species that likes to feel in control. But it might be the reality we have to accept, and paradoxically, that might be okay. The vast majority of encounters between civilizations, even with significant technology gaps, don't end in extermination. There are conflicts and injustices, absolutely, but total destruction is rare. More often, there's some form of coexistence, exchange, gradual adaptation. If aliens wanted to destroy us, they probably would have done it already. The fact that 3i Atlas, if it's artificial, hasn't vaporized Earth or launched weapons suggests intent is not overtly hostile. Observation, study, perhaps communication, but not conquest or destruction. That's cautiously optimistic. Let me also address the possibility that 3i Atlas is not from an alien civilization at all, but from a future human civilization. This is a mind-bending idea, but it's worth considering. What if 3i Atlas is a probe sent back in time by our own descendants? Time travel involves physics we don't fully understand and possibly can't achieve. General relativity allows for some solutions to equations that include closed time-like curves, paths through space-time that loop back on themselves, but whether these actually exist in our universe, whether they're practically accessible, is unknown. Most physicists are skeptical, but let's entertain the idea. If time travel is possible, if future humans develop the ability to send objects into the past, why would they send a probe to our era? Perhaps to observe a critical juncture in human history. The early 21st century is arguably a pivotal time. We're developing technologies that could lead to utopia or disaster. Nuclear weapons, artificial intelligence, genetic engineering, climate change. The decisions made in these decades could determine whether humanity survives and flourishes or collapses. A future civilization might want to study this period carefully, to understand how the pivotal choices were made, to observe the dynamics firsthand. They might send a probe disguised as an interstellar object to avoid interfering, to observe without being observed. This would explain why 3i Atlas looks partly natural but has artificial anomalies. It's camouflage, meant to blend in while still accomplishing its mission. This is wildly speculative, obviously, but it's an example of thinking outside conventional boxes, considering possibilities that seem absurd until you actually work through them. And it illustrates how open-ended the question of 3i Atlas's origin really is. We can constrain possibilities with evidence, but we can't rule things out completely until we have definitive data. Most likely, if 3i Atlas is artificial, it's from an alien civilization. That's the straightforward explanation. But straightforward doesn't mean certain. We should keep our minds open to alternatives until the evidence narrows them down. Now, let's talk about communication. If 3i Atlas is artificial, should we try to send messages to it? This is a contentious question with no clear answer. Arguments for attempting communication include the obvious one. This might be our only chance to make contact with an alien intelligence. If we don't try, we miss the opportunity. The potential benefits, knowledge, technology, insight into the universe could be transformative. Arguments against include the risk of revealing ourselves to unknown entities with unknown intentions. The dark forest hypothesis suggests the universe might be dangerous, that civilizations hide to avoid detection by predators. Broadcasting our presence could attract attention we'd rather avoid. Even if the risk is small, the stakes, potential extinction or conquest, are so high that caution might be warranted. There's also the question of who gets to decide. No single nation or organization speaks for humanity. Attempting communication with an alien intelligence is arguably something that affects everyone on Earth, so shouldn't everyone have a say? But how do you organize a global decision-making process on something this unprecedented? There's no framework for it. In practice, if someone wants to send a message, they probably just will. You don't need massive resources to beam a radio signal into space. Amateur radio operators have equipment powerful enough. So even if there's no official decision to communicate, individuals or groups might do it anyway. This lack of coordination is both a strength and a weakness. It means we're not paralyzed by bureaucracy, but it also means actions could be taken that most people wouldn't endorse. The content of any message is another challenge. What do you say to an alien intelligence? How do you encode information in a way they can decode? The classic approach is to start with mathematics, universal truths that any technical civilization should recognize. Prime numbers, pi, the Pythagorean theorem, these establish that the message is from an intelligence, not random noise. Then you might send information about us, our biology, our planet, our civilization. The Voyager Golden Records include images, sounds, music, greetings in many languages. They're meant to convey the diversity and richness of Earth life and human culture. A message to 3i Atlas might follow similar principles, though optimized for radio or optical transmission rather than physical media, but there's risk in revealing too much. Information about our location, our technology level, our weaknesses could potentially be used against us. This sounds paranoid, but when dealing with complete unknowns, paranoia might be prudent. The safest approach might be to send only the minimum needed to establish communication, then wait for a response before sharing more. Of course, if 3i Atlas has been observing Earth, which seems likely if it's artificial, they already know a lot about us. Our radio and television broadcasts have been leaking into space for decades. Anyone listening could detect them and learn our languages, see our cultures, understand our technology level. So maybe there's no point in being coy. They already know who and where we are. This is part of what makes the situation so complicated. There are no clear right answers, only trade-offs and judgments based on incomplete information. Different people and groups will reach different conclusions about what to do, and will probably muddle through with a mix of approaches, some cautious, some bold, hopefully averaging out to something reasonable. Let me address another question that comes up frequently. If 3i Atlas is artificial, why would an advanced civilization build something so large and send it on such a slow journey? With better propulsion, they could send smaller, faster probes that would arrive sooner and be more efficient. The answer might be that bigger is better for certain mission profiles. A large probe can carry more instruments, more redundancy, more fuel or propellant. It can operate independently for longer periods without resupply. It can survive micrometeorite impacts and radiation that might damage smaller probes. For a mission lasting thousands or millions of years, robustness matters more than efficiency. Also, we're assuming they have better propulsion than what 3i Atlas demonstrates. But maybe they don't. Maybe their technology is only moderately more advanced than ours. Maybe they're using the best propulsion they have, and it's still limited to speeds comparable to what we're observing. Interstellar travel might just be hard, slow, and expensive for everyone, regardless of how advanced you are. Or maybe size serves purposes we're not considering. Maybe the probe is also a seed ship carrying biological samples or digital templates for life forms that could be deployed to appropriate planets. The size allows for extensive biological storage or manufacturing capabilities. Maybe it's designed to establish long-term presence in star systems, becoming a permanent outpost or way station, rather than just passing through. These are possibilities we can't evaluate without more information, but they illustrate that our assumptions about what an alien probe should look like might be wrong. We're projecting based on our own engineering priorities and constraints. Aliens might have different priorities that lead to different design choices. Size might also be a deliberate signal. A large probe is easier to detect from far away. If the mission includes being found by indigenous civilizations in visited star systems, bigger is better. You want to be noticed, to be recognized as artificial, to prompt investigation. A small probe might pass through undetected. A multi-kilometer object is hard to miss. This connects to an interesting idea called the zoo hypothesis. The suggestion is that advanced civilizations intentionally avoid contact with less developed ones, observing from a distance but not interfering. Like zookeepers or wildlife researchers, they study without disrupting. If this is a widespread practice, it might explain why we haven't seen obvious signs of alien civilizations despite the vastness of the universe. 3i Atlas's behavior, if artificial, might fit this pattern. Observing our solar system, perhaps studying Earth, but maintaining distance, not landing, not broadcasting, not making obvious contact, just watching, gathering data, moving on. This allows scientific study without interference, letting civilizations develop naturally without outside influence. Whether this is ethical, whether it's right to observe without engaging, is debatable, but it might be the norm, the accepted practice among spacefaring civilizations. If so, we might be under observation frequently without knowing it. 3i Atlas might not be the first probe to visit our solar system, just the first we've detected. There could have been others in the past before we had the technology to notice them. Looking forward, as our detection capabilities improve, we might find more. We might realize that interstellar probes are relatively common, passing through star systems regularly on survey missions. This would be both exciting and humbling. Exciting because it means there's a lot of intelligence out there. Humbling because it means we're probably being watched and studied like specimens in a zoo. Some people find this idea disturbing, the loss of privacy, the sense of being observed without consent. But others find it comforting. If we're being watched and they haven't interfered destructively, that suggests benign intent. They're curious, scientific, peaceful. That's a better scenario than hostile expansion or indifference. Let's also consider the timeline. If 3i Atlas is artificial and did come from another star system, how long has it been travelling? At 58 kilometers per second, which is fast for a physical object but slow on cosmic scales, it would take about 20,000 years to cross 1 light year. The nearest star to us, Proxima Centauri, is 4.2 light-years away. So roughly 80,000 years to get here from there if it came from our nearest neighbour. Realistically, 3i Atlas probably came from farther away. There's no evidence of technological civilizations in the immediate solar neighbourhood. So maybe 10 light-years, maybe 50, maybe more. That's hundreds of thousands to millions of years of travel time. The probe would have been launched in the distant past, long before human civilization existed. This means the civilization that sent it might no longer exist. Civilizations rise and fall. Over timescales of hundreds of thousands of years, a lot can happen. They might have gone extinct, destroyed themselves, evolved beyond recognition, or simply lost interest in their ancient probe missions. 3i Atlas might be an orphan, still executing a program designed by creators who are long gone. That's a melancholy thought, but not implausible. It would mean we can't communicate with the builders, can't establish dialogue or exchange. We can only study the artifact they left behind, but even that would be valuable. Even a relic tells us something about its makers, their technology level, their scientific interests, their engineering aesthetics. We could learn a lot from careful study. Alternatively, the civilization might still exist and 3i Atlas might be in communication with them. But the communication would be very slow. If they're 50 light-years away, a radio signal from the probe would take 50 years to reach them. Their response would take another 50 years to come back. A round-trip conversation time of a century. This makes real-time interaction impossible, but it doesn't prevent communication entirely. The probe might transmit periodic reports, sending data back to its home civilization. Decades or centuries later, the information arrives, and they learn what the probe discovered. From their perspective, it's archive research, studying ancient data about star systems visited long ago. But it still has value. From our perspective, if we intercept these transmissions, we might be able to decode them. We might learn what the probe is sending home. We might even be able to insert our own messages into the data stream, piggybacking on the probe's transmissions to send information back to its creators. This is highly speculative, but it's a possibility worth considering. All of this assumes interstellar communication is practical despite the time delays. For species with long lifespans or stable institutions that persist for centuries, it might be. They could engage in projects that span generations, accepting that results won't be seen in any individual's lifetime. Humans struggle with this because our lifespans are short and our institutions fragile. But a civilization that thinks in millennia might find it perfectly reasonable. This brings up another point. If we did establish communication with 3i Atlas's builders, assuming they still exist and we could decode their messages, what would we talk about? What information would we exchange? The obvious starting point is mutual introduction. Who are you? Where are you? What do you like? Basic facts about our respective civilizations. Then perhaps scientific knowledge, mathematics, physics, chemistry, the universal languages of the cosmos. We could compare notes, see where our understanding aligns and where it differs. They might know things we don't, and vice versa. Even a civilization far more advanced than us might not know everything. Different lines of inquiry, different priorities, might lead to complementary knowledge. There could be cultural exchange too, though that's harder because culture is specific to biology and history. But art, music, literature, philosophy, these might translate across species boundaries if we put in the effort. Understanding how aliens think, what they value, what they create, would be fascinating even if direct translation is difficult. And there might be practical information. They could warn us about dangers, cosmic threats we're not aware of, or they could offer technologies, solutions to problems we face. Though whether they would do this, whether they'd want to interfere in our development, is questionable. The zoo hypothesis suggests they might prefer non-interference. But if we initiate contact, if we ask for help, maybe the rules change. Of course, all of this is contingent on 3i Atlas being artificial, on successfully establishing communication, on the builders still existing and wanting to talk. That's a lot of ifs. But even if only some of these conditions are met, even if we only get partway down this path, it would still be extraordinary. Let me bring us back to practicalities one more time. What can you, an individual person interested in this topic, actually do? How can you participate in the observation and analysis of 3i Atlas? There are several options depending on your resources and interests. If you have access to a telescope and imaging equipment, you can observe 3i Atlas yourself and contribute data to citizen science projects. Organizations like the American Association of Variable Star Observers and similar groups worldwide coordinate amateur observations of comets and asteroids. Your measurements, if properly calibrated and documented, can be valuable additions to the scientific dataset. Even without equipment, you can follow along with public data releases. NASA, ESA, and various research institutions publish observations and findings. Websites and social media accounts dedicated to astronomy share updates regularly. You can stay informed, learn about the latest observations, see how the story develops. You can also educate yourself about the underlying science, learn about orbital mechanics, about spectroscopy, about the methods astronomers use to study distant objects. This not only helps you understand 3i Atlas better, it makes you a more informed citizen capable of evaluating scientific claims critically. And you can participate in discussions, Online forums, social media groups, comment sections, these are places where people exchange ideas and information. Your questions and perspectives contribute to the broader conversation. You might raise points others hadn't considered, or learn things you didn't know. The collective intelligence of engaged communities can be surprisingly powerful. If you're artistically inclined, create works inspired by 3i Atlas. Art has always helped us process and understand new ideas. Artists interpreting first contact scenarios, imagining what alien probes might look like, or what their missions might be, contribute to cultural conversations about our place in the universe. Your work might inspire others, might make complex ideas accessible, might help people think about these questions in new ways. For those with political or organizational influence, you can advocate for policies and funding that support continued observation and study. Space science is chronically underfunded despite its profound importance. Public support helps justify budgets for telescopes, research programs, and missions. Your voice, added to others, can make a difference, and perhaps most importantly, maintain a balance between excitement and skepticism, between hope and realism. These questions about 3i Atlas and potential alien intelligence are genuinely important and worthy of serious consideration. But they're also easy to get carried away with, to let imagination outrun evidence, to believe things because we want them to be true rather than because data supports them. Stay grounded, demand evidence, be willing to change your mind when new information comes in. That's how we navigate uncertainty responsibly. That's how we participate in discovery without falling into delusion. The Jupiter encounter is coming. Soon, within months, we'll have new data that will significantly constrain possibilities. 3i Atlas will either behave naturally or it won't. It will either follow predictions or it will surprise us. And based on what we observe, our understanding will shift, our probabilities will update, our knowledge will grow. That's exciting. That's what makes this moment in time special. We're on the cusp of learning something important about an object from beyond our solar system. Whatever that something turns out to be, natural or artificial, expected or surprising, it will add to humanity's accumulated knowledge about the cosmos. And accumulating knowledge, expanding understanding, exploring the unknown, that's what we do as a species. It's what makes us human. Curiosity, the drive to know, to understand, to figure things out. 3i Atlas is tapping into that fundamental part of our nature, and that's why it matters, regardless of what it turns out to be. So stay curious, stay engaged, keep watching the skies, because whether it's 3i Atlas or some future discovery, the universe will keep surprising us. And those surprises, those moments of wonder and revelation, are what make existence meaningful. They remind us that we're part of something vast and strange and beautiful, a cosmos full of mysteries waiting to be understood.